So today we're gonna do example 7.2, and in this example, as we have discussed before, we have three methods, right? We have an equation method to solve to calculate the elastic curve or displacements. We have graphical method and we have superposition method. So we'll use equation method and graphical method today, and then next time we're gonna use these tables to directly calculate. Instead of formulating the equations, we can just directly use these equations to calculate this displacements. And if we will use these equations, that method is called superposition method. So let's start working on this example. So this says we have to use shear force bending. We have to calculate equations for shear force, bending moment, bending angle, and the displacement using equation method, graphical method, and superposition method. So we already know what equation method is. So I'm gonna just be a little brief in this method. So let's start with equation method. So first we'll use equation method to solve for this example. So what we have to do is the first step is to draw a free body diagram, right? So I'm just gonna, so this is a uniformly distributed load P naught, and you also have a moment which is called ML, and the distance is length L. So first step is in the equation method is to calculate the reaction, right? So you can use equilibrium equations and you can calculate the reaction. I'm just gonna directly write the reaction. So reactions come out to be P naught L, and the moment will be P naught L squared by 2 minus ML. So everybody knows how to calculate the reaction, right? You just have to calculate, use equilibrium equations. If you do use summation of vertical forces equal to 0, you're going to get P naught L. If you use summation of moment at this point is equal to 0, you're going to get the value of a moment. So once you have the reactions, you want to formulate the equations. So how you formulate equations is that you cut a section and you call distance x, and then you expose the internal loads. So this is what I am gonna do now. So I'm gonna expose the internal loads, which is shear force and bending moment. And we already know this is P naught. This distance is gonna be x. And reactions we have already calculated, which is P naught L, and the moment reaction we have also calculated, which is P naught L squared by 2 minus ML. So now you can calculate the equations for V and M by using equilibrium equations, right? So if you do summation of f of y is equal to 0, summation of moment is equal to 0, you can calculate the equations for the V and M. So I'm just gonna write equations directly. So let me write. So everybody can calculate the values, right? You have to use equilibrium equation. That is summation of f of y is equal to 0 and summation of moment is equal to 0. So if you do this, you can extract the value of shear force and bending moment. So you're gonna get shear force, you're gonna get P naught L minus P naught X. And moment value, you will get ML minus P naught L square by 2 plus P naught Lx minus P naught x square by 2. If anyone has some questions about this, they can ask, but all I have done is I've used equilibrium equation. So I've done summation of f of y is equal to 0. That is p naught L minus this, you're going to get this value. If you do summation of moment at this point is equal to 0, it's going to be this. And the moment arm from the load, and this moment and shear, and you're going to get this moment value. So basically, I've just used equilibrium equations to come up with this. And we also know if we want to calculate bending angle, that is 1 over EI and integration of moment, right? And if we want to calculate displacement, that is integration of bending angle. And we have used these equations before, so I'm just gonna write the final answer. So the bending angle in this case is 1 over EI MLX minus P naught L square X by 2 plus P naught L X square by 2 minus P naught X cube by 6, and you also have to put a constant. And so you can integrate this moment and you're going to get all these values. So ML, you integrate this, you're going to get MX, you integrate this, P naught L square, and then you have to put X here, which is this. You have to put X square by 2, which is this, and you have to put X cube by 3 multiplied by 2 is 6. So this is how you get the bending angle. And if you use this equation, you integrate the bending angle, you're going to get the elastic curve, which is basically equation for the displacements. And these are the values which you're going to get. This is x, so it's going to be x squared by 2, pl squared. This is x, so this is also going to be x squared by 2, and 2 multiplied by 2 is going to be 4. And then you have p naught l, this is x squared, so it's going to be cube by 3, and 3 multiplied by 2 is going to be 6. And this is x cubed, so it's going to be 4, and divided by 4 multiplied by 6 is going to be 24. And then you will have C1x plus C2. So all we have to do now is to calculate C1 and C2, and once we have C1 and C2, we'll have all the equations, and we can draw shear force, bending moment diagram, bending angle diagram, and the elastic curve. So this is a cantilever beam. So in cantilever beam, we know when x is equal to 0, our bending angle is also 0 and our displacement is also 0. At the start of a cantilever beam, you have a fixed support. And at fixed support, your bending angle is also 0 and your displacement is also 0. So if you equate this in equation 3 and 4, you're going to get C1 is equal to 0 and you're going to get C2 is equal to 0. So basically I can just cancel them out because they're not going to play a role in our case. So now you have equations, 4 equations, and now I think you guys can draw shear force and bending moment diagrams and bending angle diagrams as well, right? So this is equation method, which we have already learned before. So now let's try to use a graphical method. But before that, I just want you guys to calculate something for me. So I will just write values for the loads. So if P naught is 10 kilonewton per meter, length is 4 meter, moment is 30 kilonewton meter, and EI is 20,000 kilonewton meter square. at the end of a cantilever beam, you guys can give me shear force value, bending moment value, bending angle, and displacement at the end of a cantilever beam. So at the end of a cantilever beam, our x would be L or 4 meter, right? So use all these four equations, give me these four values. So shear force, so at x is equal to 4 meter, shear force is 0, bending moment is 30 kilonewton meter, bending angle is 0.00067 radians, and displacement is -4 millimeter. So this would we have calculated at a distance x is equal to 4, that is at the end of a cantilever. We can calculate these values at any point on a cantilever, and if you calculate at 1 meter, 2 meter, 3 meter, 4 meter, you can basically draw shear force diagram, bending moment diagram, bending angle, and the displacement diagram. So everybody is clear how we can draw the shear force and diagram using the equation method. All you have to do is like formulate the equation method using the equations. So now we already have the equations. Now what we will do is that we will use a graphical method to directly draw shear force and bending moment diagrams. But we can also draw these diagrams using these equations. But I will use an alternative method to draw shear force and bending moment diagram. So let's use a graphical method. So we have a cantilever beam. We have a uniformly distributed load of 10 kilonewton per meter, and we have a moment which is 30 kilonewton meter. I'm just inputting the values which we already know, and we already know the reactions also. This reaction was P naught L, so P naught is 10, L is 4, so it's gonna be 40 kilonewton, and the moment we already know the equation, right? So if you put the values in the equation, you're gonna get 50 kilonewton meter. So one way is use the equations and draw shear force and bending moment diagrams. Another way is just directly try to draw shear force and bending moment diagram from the beam itself. And if we just gonna use the beam, then we can say that we are using a graphical method to solve for the shear force and bending moment diagrams. So I'm just drawing at every meter, I'm just roughly plotting the values. So we know that shear force is basically integration of the load, right? So this is 40. First reaction is 40, which is upward. So shear force value is also this same 40. So whatever the reaction load is, if it's going up, shear force is 40 positive. If it would have been going down, shear force would have been -40. So this is 40. And now what we have to do is that we have to add or subtract to this 40 based on whatever loadings we are getting. So we're going to integrate the loads. So what I will do is that I have divided this 4 meter beam into 4 segments. each of 1 meter, right? So this is 1 meter, this is 1 meter, this is 1 meter, and this is 1 meter. So what we're going to do is that we're going to integrate the loads at each meter. So if you want to sum up the load, so this is 10, right? 10 multiplied by 1. So this total summation of load in this 1 meter beam is actually 10. This is also 10. This is also 10. This is also 10. So I have basically added, so I have integrated the loads. So this is 10 kilonewton per meter, right? So 10 kilonewton per meter. At every meter, I have 10 kilonewton of force. So if you want to calculate shear force at this point, what we have to do is that we already have a shear force 40, and then we're gonna subtract this value 10. So 40 minus 10, you're gonna get 30. So if you want to calculate shear force at this point, you're gonna add and subtract everything that happened before. So before you had a force 40, which is going upward, and then you had a negative force 10 going downward. So 40 minus 10, you get the 30 value. If you want to calculate shear force value at this point, so everything that happened before in terms of loading, you have to add, you have to integrate all the loads before this point, you're going to get this value. For example, this is 40, right? 40 minus 10, you're going to get this point. So 40 is going upward. These loads are going downward. So 40 minus 10, you're going to get this value, which is 20. If you want to calculate at this point, you're going to get 40 minus 10, which is 10. And at this point is 40 minus 10, so you're going to get 0. So that's the shear force diagram. And you can also use equation method to calculate the shear force diagram. We can just roughly do this. So equation is P naught L minus P naught X. So the shear force equation is P naught L minus P naught X, right? So if you put X is equal to 0 in this equation, your shear force is 40. You can try and you can calculate, you're going to get the 40 value. If you put X is equal to 1, you're going to get 30 value. So remember, I asked you to put X is equal to 4 to calculate the shear force, and you got 0 value, right? This value. So you can also use equation, you can also use graphical method. So graphical method says wherever you have to calculate the shear force, you have to add and subtract all the loadings that happened before, and if you accumulate everything, you're going to get 1 point. For example, if you want to calculate this shear force value, you go up, everything before, you just have to accumulate, and whatever value you're getting is this value. For example, at this point, you have a shear force which is going up, and then you have a force, loading force, which is going down. This is also going down, this is also going down. So 40 minus 30, you're going to get 10. So that's how you can calculate the shear force. So is it clear, or is it a little confusing? Okay. So now we will calculate bending moment. And bending moment, the concept is same. You have to, if you want to calculate bending moment, you're going to integrate shear forces. Before you were integrating loading, now we're going to integrate shear force to calculate the value of moment. But in the start, we have to figure out what's the value of the moment, right? So I'm going to give you one convention to figure out if the bending moment is negative or positive. So if you have a bending moment in this direction, and if you have a bending moment in this direction, Can you guys let me know that what would be the deflection in this case and what would be the deflection in this case? Can you imagine the deflection? If you have a bending moment here, the beam is gonna deflect something like this, right? If you have a moment here, it's gonna try to pull this simply supported beam upward this moment. So if I draw the elastic curve for this, you're gonna get this type of bending. If under this moment, you're gonna get this type of bending. So this type of bending is called sagging. And this type of bending is called hogging. And sagging, we have assumed positive. And hogging, we're gonna assume negative. That's just the convention to draw the shear force and bending moment diagrams graphically, or yeah, I mean, using the equation method. So that's the convention which we're going to follow. If the beam is bending in a sagging position, then you're going to go positive. If the beam is bending in a hogging position, you're going to go negative. So in this case, this moment is going to cause sagging or is going to cause hogging. Whoever thinks it's going to cause sagging can raise their hand. Whoever thinks it's going to cause hogging can raise their hand. Okay, good, good, yeah. So hogging is negative, so I'm going to go negative. So this is minus 50, right? Like before, we had a shear force 40, so we go up 40. Now we are determining the bending moment diagram. So 50 is the moment. I'm going to go down 50. So this is negative 50 moment, right? So now, before also we were calculating the areas. Now we also calculate the areas for the shear force. So what I will calculate this area and I will put it here. I will calculate this area. I will put it here. This area here and this area here. So you guys can also try to calculate the areas. So this is a trapezoidal shape. You can use the formula a plus b by 2 into c, or you can divide this trapezoid into triangle and rectangle and calculate the area as well. And you can try to calculate the area. If you calculate the area, this is what I'm getting. I'm getting 35 for this, 25 for this, 15 for this, and 5 for this. So yeah. So if you want to calculate the bending moment at this point, either you can use equation and put x is equal to 1 in the moment equation, you're going to get the moment value. Or you can calculate the area, all this area, and the moment before, and then you're going to get this value. So you have negative moment, right, negative 50, and this is positive. This shear force is actually positive. So all these values are positive. So minus 50 plus 35 is going to give you this point, which is this point, which is negative 15, right? 50 minus 50 plus 35 is negative 15. If you want to calculate this point would be everything that happened before, right? You have already a moment minus 50. Minus 50 plus 35 plus 25 will give you this point. Minus 50 plus 35 plus 25 is going to give me 10, right? Similarly, minus 50 plus 35 plus 25 plus 15 is going to give me this point, which is 25. And then if you add everything, you're going to get 30. And remember, when we use x is equal to 4, we got 30, right? This is what we got, which is the same from the graphical method as well. Now you have to just join the dots and you can get the bending moment. So this is bending moment. So this part is basically negative and all this part is positive. Yes. I mean, it's at the very end, so it's already like you can add if you add this, you're gonna get zero, right? So it's already in God. It's already. So this is causing hogging, or this is causing sagging. I would say this is causing sagging, right? So that's the 30. So yeah, yeah, it's already included. Yeah, I mean, I got yeah. So basically, because this 30 is already included in the reaction, right? So that's how you're gonna get. This is a very good question, but it's already included because that. So you're supposed to get 30 at the end because you have a moment 30. Yeah. So we don't have to add or subtract 30 because it's already indirectly included in the reactions. But this is a very good question. But you can cross verify because at the end you have a moment 30, so you should get 30 actually. So that's how you can verify you have like right bending moment or not. So now we can move to calculate uh, bending angle. So same bending angle is basically 1 over EI, and it's basically integration of moment, right? So same process, we're going to calculate the areas, and then we're going to use these areas to draw the bending angle. So what I want you guys to do is you can calculate this area here and these areas and let me know what are the values of these areas. It's not going to be accurate because before we had a straight line. Now this line is not straight. This is a little curve, but you can assume that this is a straight line. So you have to convert basically this into a triangle and a rectangle, and you have to calculate the areas. So you can calculate the areas and let me know what are the values of those areas. So far, is it clear or is it little confusing and difficult? Little confusing, right? All right, so you can calculate the areas and let me know. And this is a cantilever beam, and we already know at a fixed support, our bending angle is going to be 0. And if we want to calculate the displacements, we also know that the displacement at a starting point is going to be 0 because it's a cantilever beam. For the bending angle, and this is what I'm getting for the so I guess this point is minus 32.5 over EI because now we have EI also. This is going to be, this point is going to be minus 16.87 over EI, and this point is going to be 10.63 over EI. And this distance we have already calculated, which is 4 millimeter, right?